Hello, my name is Thomas Attenberger. I am Sales Manager at Instrument Systems. And in today's presentation, I would like to give you an introduction on micro-LED wafer probing. Let me start with the introduction to micro-LEDs. Micro-LEDs are tiny self-emitting LEDs. Typically in sizes between 100 to 300 micrometer, we call them mini LEDs. And for sizes of 100 micrometer and below, we talk about micro-LEDs. The smallest LEDs so far are going down to 1 micrometer emitter size with a pitch of only 2.5 micrometer. In this presentation, I will not make a difference. I will just call both types of LEDs micro-LEDs. Let me emphasize that this technology is not really mass production ready yet. There are several steps which need to be optimized, especially the pixel transfer needs to have better yield in most factories. And we also know that red LEDs are prone to crack while placing them. There will be repair processes needed in case that in the final product we have defect LEDs. And what concerns instrument systems is the standard optical testing, which is not really possible for micro-LED wafers. And we have to keep in mind that each pixel of such a micro-LED wafer is still an individual light source with individual properties and therefore requires individual testing. The next slide shows a schematic process flow for LED manufacturing. This may be different from manufacturer to manufacturer, but the basic steps are more or less the same. LED testing, optical testing, takes place usually at 3 different steps. First, the full wafer testing, which can be done after the EP layers have been deposited, and it's usually done before or after chip patterning. At this position, we don't have electrical contacts, so we need to have a contactless excitation, either by laser or by strong light sources. This way we can excite all LEDs on the wafer at the same time, and a complete wafer can be tested with one or very few camera measurements. This whole process is still in a very early research phase, but we know that many companies are looking into these possibilities because it will speed up the whole process quite a lot. Then we have the standard wafer level testing, which is done after chip patterning, usually on the wafer or on a blue die. And this can be done either by single die testing or, as it's done at most manufacturers, with multiple contacting of dies. So 4, 8 or even 16 LEDs are contacted at the same time and then tested simultaneously. Then we have a third step, the package testing, where final packaged LEDs are tested. This is not really applicable to single micro LEDs because there are simply usually no packaged micro LEDs. So we see that most of the testing of the micro LEDs will take place at step 2, wafer level testing. And we will see in the next slide why these are special requirements and why there are special challenges to this wafer level testing of micro LEDs. So why is testing of micro LEDs a challenge? Well, you could say that micro LEDs are just small LEDs. This is true, but we have seen that micro LEDs are really tiny. They are going down to 10 by 10 micrometer and even smaller than that. However, we know that smaller LEDs have lower efficacy, and probably for this reason, micro LEDs will usually not go down below 5 micrometer for most applications. Still, these small sizes require new production processes throughout all the production steps and throughout the value chain. Also in our field, the optical test and measurement, we will need new technologies. There are, for example, no single package micro LEDs available. Many LEDs will be on a monolithic display module, basically, which also requires special testing procedures. And as we have seen, a lot of LEDs will be again on the wafer level. And we have seen that single micro-LED testing is too slow. Let's go to the next slide. What are the main challenges for testing mini and micro-LED wafers? Again, we will do most testing on the wafer. Usually this will be done on a non-stretched blue tape in order to reduce area distortion. Because the tape is not stretched, this will result in very narrow gaps, which will lead to special requirements in optical resolution to separate the different micro-LEDs from each other. Then we have simply huge numbers of dies on the wafer. A fairly small 4-inch wafer can already hold up to 5 million LEDs. And if we assume a 50 millisecond test time for each LED, this will amount to 2.5 days testing time just for one wafer. And this is simply too long and not acceptable to the industry. The small size brings special requirements on its own. With the small LEDs, we will have very small contact pads, and this makes contacting by needles on the wafer very difficult. For non-flip chip dies, we have a large fraction of light which is blocked by the needles, and this will also make the optical results less reproducible and less accurate. And then we have very different light levels. They can range from very high levels, even at low currents of 100 microamps. We have already luminance levels of 30,000 candela per square meter. On the other hand, LIV curves start from 1 microamp, and there the light levels can be very low. Now let's take a look at the classical wafer probing setup with the integrating sphere. The sketch on the right side shows the integrating sphere placed above a wafer, which is contacted by a probe card with needles. This setup allows to test the optical and electrical parameters of each die at the same time. And basically you do a one-by-one sequential testing of all dies until all dies on the wafer have been tested. This is a proven method for standard LED wafers, and typical test times are in the range of 1 hour for regular LEDs. Now, with a huge number of LEDs on a micro-LED wafer, this process is way too slow for micro-LED wafer testing. Therefore, we need a new approach, and we have come up with the following solution, which is highly parallel testing with a camera. And the big advantage is that a camera can detect many dies at one time. And this way, an increase of testing speed is possible, and it can be a very big increase, as we see on the next slides. A little drawback is that we need multi-die probe cards, and the more dies you want to contact with a probe card, the more expensive and the more troublesome these probe cards can get. But basically we have done tests up to 256 dies in a single measurement with a 16 by 16 probe card, and this was very successful. Regular machine vision cameras are actually not very suitable for this process because they are not able to do calibrated measurements, and therefore you don't get accurate and reproducible photometric or colorimetric results. Instrument Systems has come up with a new type of camera, the Lumitop 4000, which seems to provide the ideal solution for these production requirements. First of all, it provides a high accuracy photometric measurement, and in the combination with the RGB camera, you reach the accuracy of a spectroradiometer for colorimetric measurements. Now let's take a look at the Lumitop 4000 operating principle. The Lumitop 4000 consists of a fast RGB camera, CMOS-based, for the spatial color information, and it's combined with the spectroradiometer for the spectral reference and accuracy. The spectroradiometer measures the central spot of the display and gives a reference measurement with a highly accurate data. This way, we have a spectrally enhanced RGB camera, and this has been proven in display production many times already. We have thousands of systems installed in high-end display production. And it seems quite natural to transfer this to wafer probing. Now, the big advantage of the Lumitop 4000 is that you have very fast measurement, you have very accurate measurement, and everything in 2D. And the 2D measurement capability brings a big speed increase. The color calibration is matched or can be matched to the spectrum of a DUT. And we are even providing now a live calibration, which will adjust the calibration to the DUT on the fly. For example, if the wavelength of the dyes changes across the wafer. Now, how does this improve measurement speed? Take a look at the table on the right side, and there we see the testing times for a different number of dyes in different probe card sizes, and we see that the testing time goes down to a mere hour for a 16 by 16 probe card. And that's actually a huge increase because we have calculated or simulated the testing time with the integrating sphere, and there we come up with 42 hours of testing time for a 6-inch wafer. This means that at the end, a Lumitop can replace up to 42 test stations equipped with integrating spheres. And the limitation of these numbers are not given by the Lumitop. With the Lumitop, you could measure hundreds and thousands of LEDs in one shot. The limitation is actually given by the size of the probe cards, and the larger the probe card gets, the more expensive it will be and the more troublesome will be its handling. So somehow these 16 by 16 die probe cards seem to be a good compromise of probe card size and testing speed. You should also remember that for each die you want to test, you need one source meter, but there are manufacturers who provide source meter arrays, which can be used for this application very well. You can even improve speed further by using even larger probe cards, by using faster wafer probers, or maybe work on the image processing to improve that. The next slide shows us how such a setup can look in a schematic. We see the Lumitop sitting underneath the wafer prober table, underneath the chuck. The dies on the wafer lies on the wafer chuck and is contacted by needles. The Lumitop is connected to a spectrometer, custom spectrometer, and the Lumitop itself is sitting on an XYZ positioner for fine positioning. Then we have the SMU array, which contacts to the needles, and we have two system controllers for the Lumitop and for the wafer prober itself. Now this looks very simple, but if we go to the next slide, we see what such a setup can look in production. And this is a lab setup. This is not actually a production setup, and it can look quite messy. You see at the lower center of the picture, you see the Lumitop sticking out of the table, looking up to the wafer. On the upper left and right corner, you see the SMU arrays. And in between, there is somewhere the needle array and the micro LED wafer, which can not be seen on this picture actually. Now we have to take a look at the different testing methods. We have talked about sphere testing so far and camera testing. Another question comes up, how do you compare these two testing methods? First of all, the sphere measurement, that's the standard testing of LEDs and even bigger luminaires. And since it's the standard test method for all bigger luminaires which are used in illumination, this is also the preferred testing method for LEDs used in illumination applications. The brightness and the color are averaged across all directions by means of the integrating sphere, and the result is total luminous flux, and this total means averaged over all directions. Now, micro-LEDs are usually used in displays, not in luminaires, and they are directly viewed by the human eye. Therefore, brightness and color are determined by an on-axis viewing geometry, and the displays are measured in luminance, candela per square meter, not in lumens. Now, the camera setup down here resembles very closely the direct viewing by the human eye. It's an on-axis viewing setup, and the results are also in luminance, candela per square meter. Now, how do these measurements compare to each other? Basically, we have the same DOT to measure, but we have different measurement setups for this test. Therefore, both test setups deliver different results. Simply, the sphere measures total luminous flux in lumens. The Lumitop measures luminance in candela per square meter. And you have to know that both quantities cannot be easily converted into each other. You need to know the spatial emission characteristics if you want to do so. And the spatial emission characteristics can have small deviations from dye to dye. And that's especially true when the needles are in the field of view, because these will affect the individual emission of each dye. Also, the colorimetric quantities will show small deviations. Now we have done some test measurements to compare these two test setups in the lab, and we have done that with the RGB display module equipped with mini LEDs for easier comparison. The left picture here shows the setup with the integrating sphere. It's actually a 75 millimeter PTFE sphere on top of this mini LED display. And the center picture shows the Lumitop 4000 setup with the same mini display. On the right hand side you see the test patterns for blue, green and red LEDs. Now these are the results we have received, and basically what you see here is the relation between luminance measured with the Lumitop and luminous flux measured with the integrating sphere. So basically this is on the x-axis. It's also normalized to 1 because the individual value is not really necessary to know. But what we see is that we have certain fluctuations on this dye, and this is not just measurement uncertainty. These are significant differences of this relation for individual dyes. And we see that some dyes have a fairly high ratio and some have a fairly low ratio. So it's not easy to convert these values into each other. And basically the same is more or less valid for all colors. We have done the same measurement for color measurement, chromaticity measured with the Lumitop versus chromaticity measured with the ISP. And here you have to look especially at the red lines, which show that there is a significant offset for most colors and for most coordinates, color coordinates. From the 0 line, 0 we would have if both systems come up with exactly the same chromaticity values. But there is a difference, there is an offset for each of these measurements, simply due to the different acceptance angle which is received by the camera or by the integrating sphere. Now we come to the question, who is right, the Lumitop or the sphere? We have the same wafer, but we have two different test equipments, the Lumitop and the integrating sphere, and we have two different results. Now, who is right actually depends on the application. The integrating sphere is usually used for LEDs, which are to be used for illumination. So if you have LEDs for luminaires, for backlight modules, or similar applications, then we would recommend to use the integrating sphere for their measurement. On the other hand, if you want to build displays, built with LEDs selected by integrating sphere, then you may get a poor image quality because the integrating sphere is simply not suitable to the display application. Therefore, the Lumitop is recommended for display testing or for display applications because the measurement geometry is similar to viewing with the naked eye. Therefore, it's the recommended method for all LEDs which are directly viewed. In this way, you have a new testing procedure which will result in an improved display quality by the Lumitop testing. One question which I would also like to address here is a question of color accuracy with varying micro-LED spectra. We know that LED properties can change across the wafer. We see the peak wavelengths can shift by several nanometers from one end of the wafer to the other end. We also see that sometimes spectral shapes might be a little bit different, and this will also result in color change. The current solution is that we have a color correction matrix, which is basically built into the Lumitop software, and this one is created during our calibration. The standard color correction matrix, the standard CCM, is optimized for a reference display, which is used during the calibration procedure at instrument systems. It can be adjusted to certain monochrome LED spectra, and this, however, requires a recalibration with each new LED type. However, I would like to announce here that we will soon have a feature which is called Live Call, which will provide an auto adjustment of the color correction matrix to the actual spectrum. The CCM is automatically determined according to the spectrum in the center spot, and it allows an automatic adaptation to changing spectra across the wafer. In this way, you don't have to recalibrate your Lumitop again if you go to different LED types. Another topic for micro-LED testing on wafers is that you have to come up with a solution to identify individual dyes and assign each dye individual luminance values and color values. Now, the micro-LEDs on the wafers usually have very small gaps. We have discussed this before. And the image quality is usually not very good because we are working close to the resolution limit of the system, and therefore it is often difficult to identify the individual dyes. You see the pictures on the right side. This is actually 8x2 dye array on a wafer, and you see the upper picture shows the full Lumitop picture, and the illuminated array, the real measurement array, actually is only a very small fraction of this picture. So you have to zoom in and you see that these individual dyes are very close to each other, and it's not so simple to identify each individual dye. Therefore, we have come up with a single pixel evaluation algorithm, so-called SPE algorithm, which automatically determines the grid pattern and the active area. And it also assigns photometric and colorimetric values for each cell. And ideally, this algorithm should be fine-tuned to each setup for best results. The next slide shows an effect or a procedure which we call pixel isolation for small structures. We have seen that the dyes can be very close to each other, and it may be difficult due to the resolution of the system to singulate each individual pixel. We have come up with the procedure of pixel isolation, and this means that only 1 out of n dyes is switched on to increase the dark area around each dye. N can be set to any larger number, typically 2, 4, 9 is possible, and this is actually necessary if the dyes or gaps cannot be resolved optically. It also contributes to a reduced crosstalk and heating effect, so you also get better results for individual LEDs, and you have relaxed spatial requirements for the probe card, which can make the probe card a little bit cheaper. The pixel isolation actually does not slow down the whole process as you could think, because you are only measuring every other dye. But at the end, the number of dyes per measurement remains the same, and therefore the total speed is not reduced. Now let me come to my last slide. I would like to summarize a little bit what we have learned during this presentation. Well, we have seen that the main challenges in micro-LED wafer probing are the small size and the huge number of LEDs on the wafer. The Lumitop 4000 can help to speed up micro-LED wafer probing significantly. Remember, 42 hours with the integrating sphere, only 1 hour with Lumitop 4000. Therefore, one Lumitop can replace many sphere test stations. Just one comment here, the Lumitop 4000 with our standard 100mm lens works well down to 30 micrometer die size. The camera testing is always superior to sphere testing when you are testing LEDs for displays. And the Lumitop principle with the reference to a high-end spectroradiometer ensures the highest measurement accuracy with a full traceability to national labs. Thank you very much, and goodbye.